So Dalton established that we've got these smallest particles, right? Well, then of course scientists go on and study these some more. So the idea of the atom was back in 1808, and here comes J.J. Thomson. He lived 1856 to 1940. He discovered a smaller particle. What? If the atom is the smallest piece of an element, how can there be smaller particles? This was a big deal. They were able to figure out that the electron had a negative charge on it, that it was much smaller and lighter than the atoms, and that it was uniformly present in many different kinds of substances. So they could find electrons in pretty much any element that they looked at. It seemed like all the atoms had some electrons inside of them. And so then it's, well, let's try to figure out, there's this atom, and inside of it are electrons. What else is in there, and how are these things arranged? So Thomson proposed that the electrons were held in a sphere of positive charge that balanced the negative charge of electrons. They knew that atoms were neutral. They had no net charge. If they have negative particles in there, then there must be some positive particles in there as well. So this was called the plum pudding model. And here's a picture. So this pink stuff is this sphere of positive charge, and then the electrons are just random in here. Now, in the United States, we're not familiar with plum pudding. Thomson was British. The closest thing we have would probably be a blueberry muffin. So this is a blueberry muffin model of the atom, where the blueberries are the electrons, and the muffin part is that positive sphere. So the blueberries are just kind of random inside. 1904, Ernest Rutherford was studying some of these same things. He was actually trying to confirm Thomson's experiments and conclusions. And so he did what's now known as Rutherford's gold foil experiment. So he took a source of alpha particles, which are tiny positively charged particles, and he directed this beam of alpha particles at a very thin gold foil. And then he has this detector around the foil, and this can detect if those particles go through where they went, because the particles are too small to see. But they make little tiny specks of light when they hit this detector. So what they found was that most of the particles went straight through the foil, but some of them bounced off, almost, back at you. This was not what he expected. Here's the plum pudding model. And the alpha particles are much bigger than the electrons. And so he expected that most of the alpha particles would just go straight through. They're positively charged. They shouldn't interact with the positive charge of the sphere. If anything, they're just going to shoot through it. What happened, though, was they bounced back. And this is a quote from Rutherford. His result was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Imagine taking a cannon with a 15-inch cannonball, shooting it at a piece of tissue paper like they wrap presents in. What would you expect it to do? Just blast through that paper and keep going, right? No, it bounces back and hits you in the face. Would you be surprised? I'd be surprised. You'd probably be dead too, but you'd be surprised. So then the question is, how the heck does this happen? So they had to adjust their hypothesis. They had to alter the model. And so they came up with the nuclear model of the atom. If those particles are bouncing back, they must be hitting something, and they must be hitting something that's pretty massive. So this led to the discovery of the nucleus. The nucleus contains protons and neutrons and almost all the mass of the atom. The electrons are very tiny, tiny things swimming around in this open area here. So those positively charged alpha particles, when they hit this nucleus, which is incredibly dense, they bounced off. If they got kind of close to it and dinged it, they'd get sent off at an angle. Most of the particles go straight through because there was really nothing for them to hit. So this led to the nuclear theory of the atom. Most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space, through which the tiny negatively charged electrons are dispersed. The number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles inside the nucleus. So the atom is electrically neutral. Those positively charged particles are called protons. Of course, there was a lot more work and study, and what they eventually settled on was that the nucleus has positively charged particles, the protons, but there are also some neutral particles in there, and those are called neutrons. The nucleus is more than 99.9% of the mass of the atom, but only occupies a small fraction of its volume. It's helpful to think about analogies. So you've all seen football fields, right? They're big, right? So if the nucleus was the size of a green pea, we had peas for dinner last night, they're about that big. If the nucleus was that big and I set it on the 50-yard line, the edge of the atom would be at the goal lines. 99.9% of the mass is in that little pea, and the rest of it is 0.1%, mostly empty space. To give you an idea of how dense that nucleus is, if you were able to, we can't, but if you were able to just take nuclei without all that space around them and gather them together so that it's the size of a period in your textbook, it would weigh millions of tons. That little teeny tiny amount. These electrons are distributed throughout this large region, but they have very little mass. So the electrons are a little bit like the water droplets in a cloud. You think about fog, right? Fog is basically a cloud that's down here on the ground, and we have fog every winter. You can walk through the fog, right? The fog doesn't seem to have mass. It doesn't really seem to be very solid, does it? The electrons are like those little tiny water droplets suspended in the air. But most of the fog is really empty space, and most of the atom is empty space. Protons and neutrons have very similar masses. Let's make another column here. Relative mass. Because it's really the relative mass that's more important to us. The relative mass of a proton and a neutron are 1. They're essentially the same. Here are their actual masses, 1.67262 times 10 to the minus 27 kilograms. That's an awful lot of zeros. And the neutron also, very, very close in size. So usually we just think of them as being equal in mass, 1 and 1. And then we have the electron. The electron is much smaller. It's roughly 1 over 2,000 times as big as the others. So much, much smaller. For most purposes, we can say it has no mass. A great t-shirt. Electrons have mass? I didn't know they were Catholic. You guys aren't any fun. Okay. Charges. Protons positive, neutrons neutral, electrons negative. That's actually not that hard to remember. Proton and positive start with a P. Neutron and neutral start with nu, right? Something's got to be negative. It's the other one. It's the electron. Okay? +1, 0, -1. So you need to know that. You need to know the charges. you need to know the relative masses and the names of these guys. Now, here we're listing the mass in a funky unit called atomic mass units. The atomic mass unit is abbreviated AMU. It's not a relative of an EMU. It's 1/12 the mass of a carbon atom with 6 protons and 6 neutrons. This is a unit that was made up to be a convenient size. And that sounds a little flippant. They made up a unit. Where did all the units come from? Somebody made them up because they were useful. So, atomic mass units. So these relative masses are very close to the masses of these particles in atomic mass units. Here's an interesting comparison to this proton versus the electron. If the proton had the mass of a baseball, an electron would have the mass of a grain of rice. So here, this would be the size of an electron relative to the proton. And the protons are all squished together in the nucleus, and these little tiny electrons are spread out in a very, very large volume. The proton is nearly 2,000 times as massive as an electron. So if atoms are mostly empty space, why do things made out of atoms look solid? This table here, this podium, seems pretty solid, right? I mean, I could hurt myself trying to bang my hand through there. My hand feels pretty solid. I can't see through it. How does that work? Well, matter appears solid to us because the variation in density between that incredibly dense nucleus and the mostly empty space around it is on such a small scale that we can't see it. So think about like a jungle gym or scaffolding. If you look at it, if you're right up next to it, you're right on the size scale that it is, you see that there's lots of empty space in there, right? But if you back up and keep backing up and backing up, now it appears to be solid even though it's open. So there are charged particles inside of atoms. We have to have a basic understanding of electrical charge. Electrical charge is a fundamental property of protons and electrons. They can't lose their charge or gain charge. They are charged, in a sense. When we're talking about electrical charges, opposite charges attract each other and like charges repel each other. Electrical charges act a lot like magnets do. We have more experience with magnets. I almost said maggots. That would be the biologists. Some of you maybe played with a cool toy called magnetics when you were a kid. Some of you might still play with those. My brother, who's an engineer, likes those. Or maybe you played with Brio trains with the little magnets. Or at the very least, you stuck things on the refrigerator with magnets, right? If you get two magnets, they have a north pole and a south pole. And if you try to stick the two north poles together, they oppose each other, and it's really hard to push them together. If you turn one of them around so that you've got north and south, now they stick together, right? Charges do the same thing. If the charges are opposite, positive and negative, they'll stick together, they'll be attracted. Two negatives or two positives, they're going to repel each other. And charges add like numbers do. If we have a positive charge and a negative charge, they're attracted to each other and stick together, and then overall they have a charge of 0. So that's your basic lesson in electrical charge.